Hello everyone again and welcome to the Dajo Merit Science Institute TMSI channel, and it's truly a pleasure to actually have you all in this particular space. And in here we're going to explore total electron count using quantum numbers, and in this video we were given a specific example, and in this example our goal is to be able to go back, creating a plan, thinking about all the quantum numbers and looking at multiple ways to actually approach this particular question. In here, we have the maximum number of electrons in a shell with the principal quantum number equal to 4 is what? So, let's go back to the plan. Looking at the plan for this particular problem, in order for we to get the solution, we need to keep things in mind. One is that we're asked to find the maximum number of electrons, and so our end point here is the maximum, which I'm going to highlight here as max number of electrons, and that is present in the shell with a principal quantum number. And so we're going to start off in this case with the principal quantum number, and we're going to go all the way to the maximum number of electrons. So let's look at the following steps we need to take into account. So the steps that we're going to follow is, first, we need to know what the principal quantum number is by looking at all possible quantum numbers first. Will allow us to check out various ways to go about this particular problem in order for we to get to the maximum number of electrons. So one way is looking at, first, the principal quantum number, which is represented in quantum as n. And another way to go about it is by doing the angular momentum, which is represented as L. And then our next one is, you can also use, is the magnetic quantum number, which is represented as ML. And finally, you can use the spin quantum number, which is represented as MS. So let's look at each of the following and dive really deep into the specific properties, and then explain how each of them actually works in determining the maximum number of electrons in the principal quantum number. So for principal quantum number, we know that this is actually represented as n, which means that this actually explores the size of atom, mainly speaking of the particular region. Specifically, it is the orbital itself. So the size of the orbital is the main factor that contributes to the principal quantum number. And here we need to actually take into account that n are positive integers going from 1. For in this case here, we'll go all the way to 7. It could go further depending on how many more elements we discover on the periodic table. But according to the periodic table, the n is highly associated with the period. So there is a specific formula that can be used to actually determine the number of electrons using the principal quantum number. And the formula that is going to be used is represented as 2n to the power of 2, where n is actually the principal quantum number. And from the question, we know that since n is equal to 4, we put 4 in our equation right here to determine the max number of electrons. So therefore, to get the max number of electrons, you multiply 2 by 4 to the power of 2, and this is going to give you 32 electrons. So this is one way to actually determine this particular number. And another thing here is that if you might feel that you're not sure about how to approach this particular question using principal quantum number, there is another way to go about it, which is going through the next type of quantum number using the angular momentum. And angular momentum is represented as L, and this actually shows you the subshells or sub levels in the principal quantum number. So therefore, when you have n to be the principal quantum number, well, 1 is taken away from n in our for we to get L. So therefore, in this case, for when n is equal to 1, we're going to determine how many sub-levels are found in that particular quantum number, principal quantum number of 1. So therefore, L will be equal to 1 minus 1, which is equal to 0. And the next one here is when n is equal to 2, which is when the principal number quantum number is 2, what will be the number of subshells? In this case, L is equal to 2 minus 1, which gives us 1. And then next one is n equals 3. And we know that L in this case is 3 minus 1, which gives us 2. And for n equals 4, which is our principal quantum number, L is equal to 4 minus 1, which gives us 3. Once you have this actually highlighted, there is something else that is really crucial because we need to use our L to determine the number of electrons. And to go about that, there is a formula that is called, the use of the 4L plus 2 rule. And this rule is actually used to find the max number of electrons in each of the energy levels using L. So in this case here, when L is equal to 1, you apply it to this formula. That means you have 4 times 0 plus 2. That will give us, in this case, 2 electrons is the maximum number of electrons that will be found in that particular level. And for this next one here, 4 times 1 plus 2, that will give us 6 electrons. And the next one here is 4 times 2 plus 2, that will give us, in this case, 10 electrons. And then for the fourth energy level, to find the number of subshells electrons present in that particular region, we have times 3 plus 2. This will give us 14 electrons. Excellent. And once you add all these numbers together, because we're dealing with the energy level 4 when n is equal to 4, which is a principal quantum number, what will be the total number of electrons? It means that in this case, it will have 2 plus 6 plus 10 plus 14, which will give us 32 electrons. So this is another way to actually go about using angular momentum in order for you to determine what this particular quantum number is. But the cool thing about this as well is that you can also use the periodic table to associate it with the number of electrons. And to go about this is pretty much how you're going to design it based on the periodic table setup. So using the periodic table, which is the third way to go about it, the periodic table actually is set up in such a way that is created to show all the energy levels and also all the respective L levels, which are the angular momentum. So we have this region right here, which is 1, 2, 3, 4, 5, 6, 7. So dividing it, we have all these taken care of, and we have all these right here. Hope I get this correctly, and if I mistakenly miss anyone, yeah, gotta start it over again. So after you count all this and arrange it, what we notice is that this region right here is actually known to be called the N, which is actually the energy levels that are actually available right now based on our periodic table, which goes from 1 all the way to 7. And that is how you're able to actually associate the N. And now we're going to link it to the L, which is the angular momentum, where in this particular case right here, we can actually see that this region here is associated with the number of electrons. If you count it, we have two groups, which means you have two electrons. And then in this region here, there are 10 groups here, which means that you're going to have 10 electrons going, counting from left to right. In total, it will be 10 electrons. And next one here is from here to here, which is counted as 6. So if you count number of groups, you're going to have 6. Therefore, filling fully gives you a total of 6 electrons. And finally, this region right here, counting the number of groups here, you're going to have a total of 14 electrons. So therefore, for our period, or for when n is equal to 4, which is right here, to count the number of electrons for that particular level, we're going to count this region here fully, which is the maximum number, which is 2. And then the next one here is actually going to be our 1, which is in this case, you're counting this region. And then the next one is L is equal to 2, which is in this case, we're going to count this region right here. And then the final one is this region right here where L equals to 3, which is actually accounted for at the top right there. So once you add the number of electrons that are maximum in those level for the principal quantum number 4, you'll be able to get the number 32 electrons. So this here is another way to go about determining the maximum number of electrons using the principal quantum number. And then the next one here is, how about we use the next method, which involves both combining or what we know about our ML and our MS. And what does this two represent? Our ML represents our magnetic quantum number, and this magnetic quantum number is actually linked and important in determining the orientation of our orbitals. And to determine the orientation of our orbitals, we know that they must obey a specific pattern, which is our L to negative L when we include 0 in there. So therefore, how does that look like here? For when n is equal to 1, we know that our L is equal to 0. Therefore, our ML is going to go from what? Only 0, because L and negative L is 0, 0, and 0. So therefore, we just have 0 right there. And then for the next one here is when L equals to 2, we have our L to be equal to 0 plus 1, which in this case is 1. And so our ML will be, how many different orientations are you going to have right here? We're going to have negative 1, we're going to have 0, and we're going to have positive 1. So we have 3 in here. And then for n equals 3, we have L to be equal to 2, which means since L is equal to 2, our ML will be equal to, in this case, negative 2, negative 1, 0, 1, and 2. And then finally here for n equals to 4, we have our L to be equal to 3, which in this case, ML is equal to negative 3, negative 2, negative 1, 0, 1, 2, and 3. So looking at this here, this actually shows you that in here we have, for n equals to 1, our ML means that there is no other orientation, which means that since there is no other orientation, this ML equals 0 is actually the s orbital. And then for the ml from -1 to 0 to 1, this actually has lobes that are actually assigned to the p orbitals, and the p orbitals, there are three of them, one usually on the x, y, and z. I'm really bad at drawing, but I'm just going to try my best and give a little rough sketch of those, where this is going by y, this will be rx, and this will be here our z. And then the next one here, which is ml, is equal to -2, -1, 0, 1, and 2. We have 5 suborbitals, and those actually are oriented differently within the three-dimensional space. And one of them that's kind of cool, I prefer, or I know looks really fascinating, is the one with the little ship that looks like Saturn, but not really. But then you have the in phase right here, and the other sides are out of phase, depending on which one you pick. And then the final one here is the F orbitals, and in here there are 7 orbitals in the F region, and the F region is way more interesting in terms of the design and the probability of electrons in those specific space right there. And so looking at these, we will then need our ms, which involves electron, and how this is going to be important in understanding that, hey, the electrons, they are parallel in terms of assigning, and they are opposite in directions, because in this case here you're dealing with the angular momentum and the orbit of its own axis spin, which is in positive and negative direction. And this is actually a feature that is expressed using fermions, and fermions, they have their number assigned to be half, and in this case, since it's opposite in direction, -half. And a great example of fermions are electrons in this particular space right here. So therefore, for assigning electrons, we know that we only have two electrons that are going to occupy the same space, which is the same orbital orientation. And in this particular part here, take note that if orbitals that are in the same energy level, you have to add one electron first to each orbital in the same energy level before you pair them using the opposite spin. So therefore, in this case here, for our s orbital, we only have maximum number of electrons to be equal to 2, because there is only one possible outcome, which is a spherical form. So therefore, in here, we're going to change the color to keep it kind of interesting. In here, we just have 2 up and down. This is too thick. I'll go to the next one. In here, for the p orbitals, we have 3 suborbitals, which in this case here, only one is assigned first, and then you're going to pair it up with the opposite spin. And in total here, we have 6 electrons. So in here, we have 2 electrons. This one here, we're going to have 6 electrons. And for the next orbital here, which is the d orbital, our d orbital here, we have 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, which is shown here as 10 electrons. And finally here, for our f orbital, since we have 7 suborbitals, we're going to add 1 electrons to each of them first, and then we pair up. And in here, once you add all these electrons together, you're going to have a total to be equal to 14 electrons. So therefore, in here, once we add all these electrons together, 2 plus 6 plus 10 plus 14, because we are dealing with n equals to 4 for the principal quantum number, what is the total number of electrons? In here, we're going to have 32 electrons. So therefore, in this particular video here, we're not only able to express determining the total number of electrons using quantum number principally in here, using this method through our formula 2n to the power of 2 to get 32, but also you can use the angular momentum, which is L, by first deriving the L using the N -1, and from then using the 4L plus 2 to each of the energy levels or principal quantum numbers up to the principal quantum number in question. And then you add all the electrons together to get the maximum number of electrons that will be occupied in the fourth principal quantum number. And then this actually is connected as well, not only to the periodic table in terms of the setup, where you can count each cells in the fourth energy levels, either coming from L equals to 0 to L equals 1, L equals 2, and then L equals 3. But also you can use the ML, which is a magnetic orientation, alongside the spin quantum number to be able to not only gets the other orientations magnetically that actually puts electrons, looking at how the two electrons they are actually having, or any electron in a particular atom, they all have different quantum number, which means the combination of all four quantum numbers. One electron always has a unique combination. No two electrons will have the same. That is where the Pauli exclusion principle actually comes into play in terms of the spin quantum number and how we are able to get the total number of electrons, which is in this case 32 electrons. So that's about it for this particular video. Please hit the comment down below. Let me hear your thoughts about this particular topic. If you have any questions, please don't forget to let me know in the comment section as well. And also, by that way, I can talk to you all later. And please don't forget to subscribe. By that way, I can talk to you all soon. Stay smart and believe in yourself.